Hello everyone, I am Ling Li, an assistant professor from the University of Maine. Today I'm going to talk about the research progress of using a membrane-based dehumidification system to improve the energy efficiency of kiln drying process. I will start with discussing a case study of energy consumption, then provide our solution and discuss the performance of the membrane system we proposed and the limitation we have found. I will end up with introducing our future work. Conventional wood drying process, also known as heat and wand drying, is regarded as an energy-intensive process. We did a case study to analyze how much thermal energy is used to heat the cold fresh air brought in the kiln. The wood species was eastern white pine with an initial moisture content of 120% and a specific gravity of 0.34. 1,500 board feet lumber was loaded into a small steam kiln. We followed the drying schedule developed by the U.S. Forest Products Laboratory to conduct this drying process. From this pie chart, we can see about 19% of the total thermal energy was used to heat the incoming cold fresh air. Our interest is to save this portion of thermal energy. An air-to-air heat exchange technique has been applied in some conventional kilns. However, the shortcoming of this heat exchanger is the energy recovery efficiency could be affected by harsh environmental conditions. For instance, extremely long winter season in the northern US and Canada. To solve this challenge, we proposed to develop a hollow fiber membrane-based dehumidification system to dehydrate the exhaust air from the kiln and then send this warm dry air back into the kiln. A dense PDMS membrane was selected to separate the moisture vapor from air due to its high water vapor permeability. My graduate student Nassim Ali-Kahani reported the performance of the lab-scale PDMS membrane on moisture separation in last year's SWST convention. This slide shows a brief summary. We can see the influence of 4 factors: airflow rate, initial relative humidity, temperature of the moist air, and pressure of vacuum pump on the reduction of relative humidity of the air. We found the relative humidity of the air can be decreased in the first few minutes and then leveled off, and the moisture removal efficiency is in the range of 50% to 80%, depending on the levels of factors used. Then we estimated the size of the PDMS membrane if we want to apply it in our small kiln. In step 1 of the drying schedule, we can see the ventilation rate of moist air is the highest, which is 330 kilograms per hour. The small membrane module with 1 square meter surface area used in the lab test could separate about 0.06 kilogram air per hour. Therefore, processing the 330 kilogram moist air means the membrane has a total surface area of 5,500 square meters. The size of the membrane is approximately 2.2 cubic meters. The limitation of this PDMS membrane we have identified is that it is recommended to be used in the operation temperatures below 60 degrees Celsius. However, we know most wood drying schedules require drying temperatures above this temperature. To solve this issue, we plan to add CNF or CNC into PDMS to improve the moisture diffusion coefficient. We are also developing a commercial modeling to assist in evaluating the moisture diffusion performance of the membrane to be developed. So that's all. Thank you for your attention, and I'm happy to take any questions and comments.